This is video number 5 on revision of the chemical world topic for Year 9 Science on atoms, elements, and the periodic table. Let's talk about isotopes. So an isotope is element whose atoms have a different number of neutrons. So the same number of protons, same number of electrons, but just different numbers of neutrons. Okay, in other words, the atomic number is the same, but the atomic mass is different. And if you recall, the atomic mass is the number of protons and neutrons. Okay, most of the mass of the atom comes from protons and neutrons. I'll illustrate with an example. Perhaps one of the most common examples is hydrogen. Hydrogen has 3 isotopes. Okay, 3 different forms, in other words. I'll draw them here. So there's what's known as hydrogen 1, there's hydrogen 2, and there's hydrogen 3. These numbers here are the atomic number. My bad, atomic mass, not atomic number. So hydrogen 1, hydrogen 2, hydrogen 3, they've all got the same number of protons and neutrons, which is 1. So I'll draw that for each one. The only difference is the number of neutrons. So H1 has 1 proton, no neutrons. H2 has 1 proton, 1 neutron in the nucleus. Okay, because it's got an atomic mass of 2. 1 plus 1 is 2. H3 has 1 proton, 2 neutrons. Okay, because 2 plus 1 is 3. So that's hydrogen. Okay, they've got names. H1 is known as protium, H2 is known as deuterium, and H3 is known as tritium. Okay, but you don't need to know those for the exam. I'll give you some questions to do. Suppose I'll give you the 3 isotopes of carbon, carbon-12, carbon-13, and carbon-14. And I ask you to draw them. So it's the same idea as with hydrogen. So these are the atomic masses. And here's another question. Lithium, isotopes of lithium, 6, 7, and 8. So that's isotopes. Also got asked about combustion. So combustion is a chemical reaction. So combustion is when any substance reacts with oxygen. Okay, so something plus oxygen gives you carbon dioxide and water. You've also got this combustion comes in different forms depending on the amount of oxygen available. When you've got a plentiful supply of oxygen, like that first equation here, that's called complete combustion. Complete because there's plenty of oxygen, you get carbon dioxide and water. These two here are the result of incomplete combustion, when there's insufficient oxygen reacting. Carbon monoxide is toxic, highly toxic. It's released by car fumes. And carbon, also known as soot, it's a black powderish substance. It's a pollutant as well, can pollute things like trees in the cities. That's why cities tend to be polluted a lot from carbon emissions. An example is of complete combustion, methane, so natural gas. Methane is a natural gas. If you have a gas stove at home, this is what's happening. So you're basically, when you flick the switch, you're igniting a spark, and that spark ignites, it lights up the methane gas. Okay, and that burns, producing carbon dioxide water, and I should also mention energy. Energy is the product. You get energy from that. That's how you can make your food, cook your food. Here's the chemical equation. So methane has a formula of CH4. You don't need to know this for the exam. They'll probably give you the chemical symbol for methane. Oxygen is O2, makes carbon dioxide, CO2 plus H2O plus energy. I'm not going to write the energy. Suppose they give you this and ask you to balance it. So you make a list from left to right. C, carbon, H, hydrogen, O, oxygen. Same thing on the right. Then you count. There's 1 carbon, 4 hydrogen, 2 oxygen. On the right, there's 1 carbon, 2 hydrogen, and 3 oxygen. How do we fix this? Well, go to the hydrogen on the right, turn that into a 4 by timesing by 2. Take the 2, you put it at the front. So that's 2 times all of this, H2O. Now there's 4 oxygen on the right. Now to get 4 on the left, you times that by 2 to get 4, and the 2 goes at the front, and there you have it. That's the balanced chemical equation for the complete combustion of methane. Let's do the incomplete combustion of methane. So it'll be methane plus oxygen. So let's say in this case it gives you carbon monoxide plus water plus energy. Okay. For example. So methane is CH4, oxygen is O2, carbon monoxide is CO. Mono means 1 oxygen, so there's 1, so it's O, plus H2O for water plus energy, which I'm not going to write. Let's balance this. Let's count, so there's C on the left, then H, then O, CHO. We count how many atoms. There's 1 carbon atom, 4 hydrogens, 2 oxygens. On the right, there's 1 carbon, 2 hydrogen, and 2 oxygen. Let's turn this hydrogen on the right into a 4 by timesing by 2. The 2 goes out here. Now there's 3 oxygen. So 2 and 3, what's common between them is 6. Okay, so you times this by 2 to get 6 on the right. Put the 2 out the front here, and I'll show you why. There's now 4 oxygen on the right. Now on the left, times that by 2 to get 4, and you put the 2 at the front here. And now it's balanced. So that's combustion. Let's look at the periodic table as a whole in terms of trends and patterns. So let me draw the periodic table roughly. It's like a big square, or rectangle I should say. When you go down a group, the atomic radius increases. In other words, the atoms get bigger as you go down a group. Why? Because the atomic number gets bigger. If the atomic number is bigger, there's more protons, more electrons, the atom looks bigger. Okay, atomic radius, in other words, how wide it is. Also, the reactivity increases. Okay, so let's suppose there's lithium at the top here. At the very bottom is francium in group 1. Francium is highly reactive, very dangerous. Just exposing it to air, it'll explode. So that's that. Going to the left, reactivity also increases because you're going from the non-metals on the right of the periodic table to the metals on the left, and metals are more reactive, right? And also going towards the left, the atomic radius increases. Now this may sound a bit counterintuitive because atomic number increases as you go across, right, from left to right. Why does it increase? Well, if you think about it, when there's more protons in the nucleus and there's electrons around it, the electrostatic force, so the force of attraction between the protons and electrons of opposite charge, is greater. So they would want to pull the electrons in a lot more. Okay, so it's more tightly bound. So the atomic radius decreases. Okay, think of the circle, it's getting smaller as you go from left to right. But from right to left, the size of the atoms gets bigger. So if I was to draw this here, it looks like something like this. And then it will gradually decrease as you go to the right. Okay, get the idea, I'm sure. There's also So I should have talked about this before the periodic table, but anyway, the idea of decomposition reactions. So decomposition is the breakdown of a substance into two or more simpler substances. I'll give you an example. Whenever you open up a can of soft drink, okay, you'll hear this. So this is carbonic acid. Carbonic because it's made of carbonate. Acid, it's got hydrogen, so H2CO3. You hear this sound. That's the release of this gas. That's the sound of the decomposition of carbonic acid. Carbonic acid breaks down into water, H2O, and carbon dioxide, CO2. And as is the case with any other chemical reaction, whatever you have on the left, you have on the right. There's hydrogen on the left, carbon and oxygen, and on the right there's hydrogen, carbon and oxygen. When you take limestone, calcium carbonate, say to make it into a powder, put it in a test tube, and you burn it, you get thermal decomposition. Thermal decomposition means, thermal means heat. Thermos is heat from Greek. It means you're breaking down the calcium carbonate using heat, and you get calcium oxide and carbon dioxide. Whatever one you have on the left, you have on the right. You have calcium, carbon, oxygen on the left, and on the right, calcium, carbon, oxygen. That's decomposition. Let me now talk about radioactive decay. Students often struggle with this too, and I emphasize this all the time. There's nothing complicated about radioactive decay, because all you need is your periodic table. That's all you really need, and literally reading off elements from the periodic table and using your calculator if you need to for subtractions and additions. The first type of radioactive decay explored was alpha decay. Alpha decay involves the release of an alpha particle. An alpha particle is a helium nucleus. Helium nucleus. It's got 2 protons, 2 neutrons. It looks like this. Plus, plus, 0, 0. An example is the alpha decay of uranium. So uranium looks like this on the periodic table. The bigger number, if you recall, is the atomic mass. Just think of mass as weight, okay, heavy, something heavy. That's the atomic number. Literally on the periodic table, there's a key, there's a legend, and it tells you what's the atomic mass, what's the atomic number. So you have to read it off. Suppose you need to work out what element uranium decays into, what it breaks down into in alpha decay. So an alpha particle is expressed as this, 42He. Okay, helium has an atomic mass of 4 because there's 4 particles in the nucleus, 2 protons, 2 neutrons, and an atomic number of 2. It's got 2 protons, okay, or electrons. The way you do this, work this out is, so it's like a seesaw. Every equation is like a seesaw. Whatever's on the left has to be on the right. The numbers at the top have to match, and the numbers on the bottom have to match. So something plus 4 gives you 238. In other words, 238 minus 4, that's 234. So the top numbers are fine. The bottom, something plus 2 is 92. That's 90. So you go to the periodic table now. You look up the atomic number, element with the atomic number 90, and you find that it's thorium, Th. So I encourage you to get your periodic table out now, if you can. Just to note, you can also rewrite the alpha particle as follows. I'll do another example. Suppose you want to work out the alpha decay of radium. So you can rewrite it as 42 alpha. Okay, that's the Greek symbol for an alpha particle. It's the first letter of the Greek alphabet, plus something. So as before, we need to match these numbers, top, bottom. So 4 plus something is 226. That's 222. On the top, on the bottom, something, 2 plus something is 88. That's 86. Periodic table, atomic number of 86 is radon, Rn. Give you some questions to do. I want you to work out this. Okay, so 2 questions on alpha decay, just using the periodic table, okay? So a lot of students stress with this, think it's the end of the world when they see an equation. It's really not that difficult. It's 2 steps. Simply use subtraction and your periodic table, and that's it. So that's alpha decay. Let's do beta decay. Now, beta decay is when a moving electron is released. Okay, when a nucleus releases a moving electron, an unstable nucleus. Okay, we'll do an example. Let's do 18878. Let's do platinum, the metal platinum. Let's do its beta decay. So beta particle is expressed like this: 0 minus 1e. Electrons don't have any mass. Well, to an approximation, they do have mass, very small amount, but we'll call it 0 mass. That's its atomic mass, and atomic number, it's -1 because they've got a charge of -1, right? So let's work out what this missing element is. So same thing as before. Numbers top and bottom have to match. Something plus 0 is 188. It's 188. Something minus 1 is 78. That's 79. And the element with atomic number of 79 is gold, Au. Let's do another one. Let's do thorium, the beta decay of thorium. So a beta particle is also written as like as this, beta. It's like an extended B. This is the second letter of the Greek alphabet, beta, plus something. So let's match up the numbers. 0 plus something is 234. That's 234. Minus 1 plus something is 90. In other words, 90 plus 1 is 91. Okay, because minus 1 plus 91 is 90. You can work it out on your calculator. And you get Pa, the element protactinium. I'll give you a question to do. Some questions. Let's beta decay. The easiest of all decays, third type, is called gamma decay. I'll show you why. Gamma decay involves the release of a gamma ray. A gamma ray is a high energy light ray. High energy light ray. Extremely dangerous. The most dangerous and most powerful of all types of radiation is gamma radiation. This stuff can cause cancer. This stuff is found in nuclear reactors, in exploding dying stars in outer space, in supernova. But it's a very simple chemical radioactive decay. I'll show you why. Suppose I have this. Now, gamma ray is given the symbol 00 gamma. It's a squiggle. It's the third letter of the Greek alphabet. Light doesn't have mass and it doesn't have charge. So 00. Something plus 0 is 137. That's 137. Something plus 0 is 56. That's 56. So you get the same element back, which is barium. Okay, you get the same element back, but it releases a high energy gamma ray. Do another one, 248M 96. Cm is curium, named in honor of Madame Curie, famous Polish-French chemist who did groundbreaking work on radioactive decay in the 20th century. So this M here means excited state. Whoops, up here. It's in an excited state, this curium nucleus. What does it decay into? Well, as before, 0 plus something is 248. It's 248. 0 plus something is 96. It's 96. So we get back curium. And I'll give you some questions to do. And the final bit, I'll talk about the history of the atomic model very briefly. So over millennia, I should say, millennia, thousands of years, scientists have come up with more refined, more developed models of the atom. So let's go back to Democritus, ancient Greek philosopher who came up with his model in around 400 BC, before Christ. He proposed that matter, stuff, everything around us was made of these indivisible spheres. You can't break them apart, right? Called atomos. Atomos means uncuttable in Greek. And the word atom comes from atomos, right? Everything was made of these spheres if you were to zoom into it. Then Dalton came along in 1803. He was an English chemist. Proposed the same idea, but proposed that different elements have different types of atoms. So carbon was like this, carbon was black, oxygen was like this, empty sphere, white sphere, hydrogen with a dot in the center, and so on and so forth. But he had the same idea as Democritus, just took it a step further and said that different elements are made of different types of atoms. They look different. Number 3, you've got Thomson, J.J. Thomson, 1904. He was a British physicist. Proposed the plum pudding model. Atoms were like this massive, were like a sphere with this positive charge with electrons embedded in it. Electrons embedded. This is called the plum pudding model. Okay, the pudding is the positive charge, the plums are the electrons. Then Rutherford came along, New Zealand-born British physicist, in 1911, and he proposed his nuclear model. In other words, there's this dense core of the atom, and the atom is mostly empty space, called the nucleus, the dense core, and you've got electrons somewhere around the nucleus, outside of the nucleus. And then number 5, the Danish physicist Niels Bohr came along in 1913, proposed his planetary model. Said that electrons orbit the nucleus, much like the planets orbit the sun. You can have electrons, particular orbits like this. And then finally, Schrödinger came along, the Austrian-Irish theoretical physicist, in 1926, and proposed his electron clouds model picture. So you have the nucleus, and you've got clouds around it, okay? These are electron clouds. So Schrödinger came up with this weird idea, with this mathematical model, which stated that electrons are described in terms of this funny thing called a wave function. You don't need to know this for the exam, it's just an aside thing. Greek symbol psi, capital psi. And this tells you about the electron, what it's doing, its properties. And the denser these clouds are, so the first cloud that's closest to the nucleus is darker, because that's where you'll find the electron most likely. That's where the electron is most likely to be. Okay, so Schrödinger came along with probability. He said you can't be certain where the electron is. You can say with probability it might be here. So around 95% chance it's near the nucleus, and out from the nucleus here is around a 5% chance of finding it. Because 5% plus 95% is 100%. Probabilities have to add up to 100%. So electrons exist in clouds, and there's no set orbits. They exist in this fuzzy haze. Clouds are hazy, right? Fuzzy. That's called the quantum mechanical model. Okay, quantum mechanics is the study of particles and atoms on the tiniest of scales. And that's it. That's the evolution of the atom. It gets more complex and more detailed with time.